They say intermittent fasting destroys testosterone, that restricting food intake, particularly skipping meals, sends the male endocrine system into a state of hormonal crisis. That energy restriction signals starvation, suppresses reproductive hormones, and reduces the body to a state of physiological shutdown. It is one of the most repeated claims in conversations about male health and fasting. And the biology of what actually happens, measured in controlled studies, tracked across weeks and months of consistent practice, tells a considerably more complex story. Because what happens to testosterone in the first days of fasting is not what happens at 30 days. What is measured in blood work at week 1 is not what is experienced physiologically by month 2. In the difference between a temporary hormonal stress response and a long-term hormonal recalibration is not a detail. It is the entire story. The biology of testosterone under fasting conditions is not simple. It is not linear. It is not what most people believe it to be. Let's begin. How the testosterone system works. Testosterone is not produced independently by the testes. It is produced in response to a hormonal cascade that originates in the brain. The sequence begins in the hypothalamus, where gonadotropin-releasing hormone, GnRH, is secreted in pulses. These pulses stimulate the anterior pituitary gland to release 2 additional hormones, luteinizing hormone, or LH, and follicle-stimulating hormone, FSH. LH travels through the bloodstream to the Leydig cells in the testes, where it signals the synthesis and secretion of testosterone. This 3-tiered signaling pathway, hypothalamus to pituitary to testes, is known as the hypothalamic-pituitary-gonadal axis, or HPG axis. It is a precision feedback system. When circulating testosterone levels rise, the hypothalamus and pituitary reduce their output of GnRH and LH accordingly. When levels fall, output increases. Once secreted, testosterone circulates in the blood in 2 primary forms. Approximately 2 to 3% exists as free testosterone, unbound, biologically active, available to enter cells and exert its effects directly. The remainder is bound to carrier proteins, primarily sex hormone-binding globulin, or SHBG, and albumin. Bound testosterone is not immediately bioavailable, but represents a circulating reservoir. Inside cells, so testosterone binds to androgen receptors, specialized proteins within the cell's nucleus that, when activated, regulate gene transcription and drive the biological effects testosterone is known for. Muscle protein synthesis, bone density maintenance, erythropoiesis, sebaceous activity, libido, and aspects of cognitive function. The density and sensitivity of androgen receptors in target tissues is as important as circulating testosterone concentration. This distinction becomes central to understanding what long-term intermittent fasting does to the male endocrine system. The first response: why the body stresses when the body experiences a sudden reduction in caloric input. Particularly when it has been accustomed to regular, frequent feeding, it activates a stress response. The adrenal glands increase their secretion of cortisol. The cortisol is a glucocorticoid, a steroid hormone produced in response to metabolic stress, low blood glucose, and states of perceived energy deprivation. Its physiological role in this context is appropriate. It mobilizes glucose from glycogen, promotes gluconeogenesis, and ensures the brain maintains access to fuel during periods of reduced food intake. But cortisol and testosterone exist in an inverse biological relationship. Elevated cortisol acts at multiple points within the HPG axis to suppress reproductive hormone output. It inhibits GnRH release from the hypothalamus, reduces pituitary sensitivity to GnRH, and may directly inhibit testosterone synthesis in the Leydig cells. Researchers describe this effect as gonadotropin suppression, a temporary downregulation of the reproductive axis during states of metabolic stress. Studies published in the Journal of Clinical Endocrinology and Metabolism have documented this phenomenon directly. Short-term fasting produces a measurable, transient decrease in serum testosterone coincident with elevated cortisol. This finding, the testosterone dip in the first days of fasting, is accurate, but the context in which it is typically discussed, omits a critical biological fact. It is a temporary stress response, not a permanent endocrine change. The body is not failing, it is adapting. What happens after that adaptation is where the more significant biology begins. The insulin connection. What constant eating does to understand what fasting restores in the male endocrine system, it is necessary to understand what habitual constant feeding suppresses. Every time carbohydrates or protein are consumed, our insulin is secreted from the pancreatic beta cells in proportion to the glycemic stimulus. Insulin is essential for glucose uptake and storage, but insulin is not a neutral molecule with a single effect. It interacts with signaling pathways across multiple organ systems, including the reproductive axis. Chronic elevation of baseline insulin, the state produced by frequent meals across a long feeding window, has documented inhibitory effects on hypothalamic signaling. Specifically, persistently elevated insulin impairs the normal pulsatile secretion of GnRH from the hypothalamus. The brain's ability to send its regular hormonal instruction to the pituitary, produce LH, signal the testes, is diminished when insulin signaling is chronically elevated. The result is a subtle but persistent suppression of the HPG axis. Not a dramatic hormonal collapse, a quiet, chronic, baseline dampening of the reproductive signaling cascade. Testosterone production is not maximized. The system operates below its functional potential. When fasting is introduced and the feeding window is compressed, insulin has extended periods during which it is not elevated. Baseline insulin falls. The suppressive effect on hypothalamic signaling is reduced. GnRH pulsatility can normalize. The HPG axis can operate with less chronic interference. This is not a proposed mechanism. It is a documented biological consequence of insulin dynamics that has been studied in both clinical and metabolic contexts. The hormone was not missing, it was being systematically interrupted. The receptor, where the real shift happens. Blood tests measure total circulating testosterone. They do not measure what the cells are doing with it. The biological effects of testosterone are not determined solely by how much is circulating. They are determined by how effectively that testosterone is received, by the androgen receptors that must bind it, carry it to the cell nucleus, and activate the gene transcription that produces testosterone's functional effects. Research from the University of Virginia examining men who practiced intermittent fasting found a significant result. Androgen receptor expression in muscle tissue increased substantially, even in participants whose total circulating testosterone levels remained stable or changed only marginally. The cells became more sensitive to the same hormonal signal. This biological phenomenon, receptor upregulation, means that the same concentration of testosterone produces a greater downstream effect. More gene transcription is initiated, more protein synthesis is driven, greater muscular response per unit of hormone. The analogy from an engineering standpoint is straightforward. The volume of a signal matters less when the receiving antenna is more sensitive. Fasting appears to recalibrate the sensitivity of the receiving hardware, the androgen receptor, in addition to any changes it may produce in the signal itself. This explains an observation that confuses many men who monitor their blood testosterone during intermittent fasting. Their numbers may not increase dramatically, yet their experience of energy, physical recovery, and physical performance often improves. Thus, the measurement is not the complete picture. The biological activity at the receptor level is. Aromatase, fat, and hormone conversion. Testosterone does not exist in isolation within the male endocrine system. It is subject to ongoing enzymatic conversion, and the most significant of those conversions, from the perspective of male hormonal balance, is the one mediated by aromatase. Aromatase is an enzyme encoded by the CYP19A1 gene. Its function is to convert androgens, including testosterone, into estrogens, specifically estradiol. This conversion is a normal and necessary biological process. Estrogen plays a role in bone mineral density, lipid metabolism, and cardiovascular protection in men, among other functions. The problem arises with aromatase overactivity. Aromatase is expressed in multiple tissues, but it is particularly concentrated in adipose tissue, body fat. The more body fat, and specifically visceral fat, the metabolically active fat that accumulates around abdominal organs, the higher the total aromatase activity in the body. This creates a self-reinforcing hormonal dynamic. Higher body fat increases aromatase activity, which increases the rate at which testosterone is converted to estrogen, which reduces free testosterone availability, which impairs the metabolic and physical functions that would otherwise help reduce body fat. Intermittent fasting, by compressing the caloric window and inducing an extended period of low insulin, during which fat oxidation is elevated, produces progressive reductions in visceral fat over weeks of consistent practice. As visceral adipose tissue decreases, aromatase enzyme concentration decreases with it. Less testosterone is converted to estrogen. The testosterone to estrogen ratio shifts. The net bioavailability of male hormones improves, not through increased production alone, but through reduced enzymatic loss. Growth hormone, the silent synergist. Among the most significant of testosterone's biological partners is growth hormone, GnRH, secreted by the anterior pituitary gland in pulses, primarily during the deep stages of sleep, but also in response to specific physiological conditions. Fasting is among the most potent known stimuli for growth hormone release. The physiological mechanism involves the fall in insulin and blood glucose during the fasted state. Insulin suppresses growth hormone secretion. When insulin is chronically elevated from frequent feeding, GnRH secretion is chronically blunted. As insulin falls during fasting, the inhibition is released and GnRH secretion increases substantially. Studies have documented growth hormone increases of several hundred to over 2,000% during fasting periods of 16 to 24 hours, depending on the baseline metabolic state and the duration of the fast. In the context of the male endocrine system, this GnRH surge during fasting represents a significant anabolic signal that operates independently of and in concert with testosterone. The two hormones reinforce each other's effects on tissue maintenance, metabolic rate, and physical capacity, making the fasted state hormonally richer than is commonly assumed. What long-term practice actually changes? After 30 days of consistent intermittent fasting practice, the male endocrine system has undergone a multi-layered recalibration, one that is not always captured in a single blood panel, but is measurable in its physiological outputs. Total circulating testosterone levels may be modestly elevated in some individuals and largely unchanged in others. What is more consistently documented is the change in the conditions surrounding testosterone. Reduced SHBG in some contexts increases free testosterone availability. Reduced aromatase activity from visceral fat loss improves the testosterone to estrogen ratio. Increased androgen receptor sensitivity in muscle amplifies the cellular response to circulating hormone. And the synergistic growth hormone surge during fasting windows supports anabolic tissue maintenance. The result is an endocrine environment in which testosterone, at similar or modestly higher measured levels, operates more effectively at the cellular level. Physical recovery is enhanced. Lean mass is better preserved. Energy expenditure and metabolic rate are supported by both hormones acting in concert. Inflammation, a known suppressor of testosterone synthesis at the Leydig cell level, is reduced by the same metabolic improvements that fasting produces in insulin and visceral fat. The story of testosterone and intermittent fasting is not the story of a hormone destroyed by caloric restriction. It is the story of a hormone system that, when chronically elevated insulin is removed, when aromatase activity is reduced, and when receptor sensitivity is restored, ANA functions more effectively in the physiological environment it was designed to operate within. What intermittent fasting changes is the environment in which that entire cascade operates. The body does not need to be pushed toward hormonal health. In the right metabolic conditions, it moves toward it on its own. This channel explores the science behind everyday health topics. And if you want more simple tips to improve your health and mind, make sure to subscribe, and I'll see you in the next video.